welcome to SOH, the best office hours ever, thanks to you. This is a 2023 AP Physics 1 and problem number 5, and we have rotation again. Rotation is very important, but especially knowing the basics of rotation. Let's see, we have negligible friction, something about the center of the mass that looks very complicated. We have some distance here, and okay, let's see, fine. So it says, use the frames in the video to answer the following questions. In which frame is the angular acceleration of the rod the greatest? So the basic principle that we are going to use is that the net torque equals I times alpha. Now, remember how we compute the torque. It is the distance to where we apply the force, so it's going to be this distance to the center of the mass, this distance, I don't know, call it L, doesn't matter, and then the force. Which force do we have here? We have gravity, right? We have gravity, 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 and gravity. Where do you think this torque is the greatest? It's going to be the perpendicular component of mg. So where is the perpendicular component to the vector, to the distance, the greatest? Here, right? Here we have 90 degrees. Here will be a portion of it, you know, perpendicular will be a portion of it. Here 0. Here a portion of it will be perpendicular, and here again 0. So for instance, here alpha is 0, and here alpha is 0. But here is the greatest. So in C is the greatest because the net torque is the greatest. And that's it. They want to understand that, they want to know that you understand the basic of it, not to compute things. Now, the next question says the kinetic energy, rotational kinetic energy. So we have to use the formula, which is this one. Now, don't worry about this. This is constant, right? The moment of inertia of this object, we don't know how much it is, but it's constant. Now, omega increases in time. Why? Because omega somehow is kind of initial omega plus alpha delta t. This is only correct when this is constant, which is not the case, only if alpha is constant. But you can say the following. So omega increases in time because there is a net torque. The net torque is non-zero, you know, until it reaches the bottom. So omega is maximum at the bottom. So here. So E is when the rotational kinetic energy is maximum. Okay, that's it. That's it. They need to understand that you have gotten a good understanding of how this works, not actually solving it. Now the next thing says derive an expression for the change of kinetic energy. Okay, first of all, there was no friction, so there is conservation, right? We have this. Okay, and they say the rod sphere Earth system is kind of very wordy. This is just to consider that you have gravitational potential energy here. Okay, so but they want the change. So this is going to be delta K plus delta U equal to 0 because the constant does not change. So the change of kinetic energy is going to be minus the change of gravitational potential energy. So good, because this has moments of inertia and omegas, right? But this one is the mass of the system, so minus, let's see, between what? E and A, right? So let's compute the moment of inertia at E, let's compute the gravitational potential energy at E and subtract it from this one. Okay, how much is it? Well, fortunately this is an easier computation, is mg, this is the weight, and then the height. Let's choose this as the 0, and that's okay, it's an arbitrary origin. And we know that this distance, they say, is L divided by 3/4 divided by L, yes, 3/4 divided by L, right? So, okay, yes, it's here. So then this is going to be like this, okay? That's at point E. Well, in E, in fact, is below, right? Yeah, we have it here. So it's going to be negative, okay? And then we have a mu GA, we have mg 3/4 L. So if you substitute that thing here, there, you have the change in kinetic energy is plus mg 3/4 L plus again mg 3/4 L. So the kinetic energy, let me just write it here, the kinetic energy, what you have is mg and then 3/2 of L. That's the question that we have. Okay, so yep, we have all this. That's great. And I think now the next question says why the rod and the sphere gain kinetic energy even if the Earth is not included in the system. Well, the Earth here provides gravity as an external force. So gravity is is doing work on the rod plus sphere system, and that's the reason. End of the story, and you're good. Now, what happens if we add the Earth? Think for a second. What can we do? Remember action reaction? The forces were the same. So the force of attraction, the force of gravitational attraction between the rod and the sphere and the Earth is the same as the Earth and the rod and the sphere. So the Earth feels this, but the acceleration that the Earth feels is this one. So the final speed of the Earth while this object is falling is the acceleration, right? By the time that it falls, that this thing happens, the time that this happens. Okay, that's the final speed of the Earth towards the rod plus sphere system. Okay, let's do a check. If we multiply the mass of the Earth by this speed, what do we get? We get this. Okay, which is the same as it would be for the rod sphere system. Okay, so linear momentum is conserved. Good. Now, what happens with the kinetic energy? That's interesting. All this is additional. Okay, this is like super much advanced. So the kinetic energy of the Earth at the end of this story is going to be 1/2 of the mass of the Earth, moving at that speed towards the rod and the sphere. While the kinetic of the rod sphere system is this one, right? Rod sphere system. Okay, now we can take the ratio. Let's see the ratio. Let's see how much does the Earth win in terms of kinetic energy compared to the rod sphere system. So it's going to be the mass of the Earth divided by the mass of the rod system and this quotient of speeds, the square, right? Now, if you substitute what we derive here, like approximately, like this expression here, what you have is that we basically have that this ratio is the ratio of the masses, right? We have Fg delta T divided by Me for the Earth and Fg delta T by the mass of the rod sphere system. So you can see how this simplifies to be this, which is much less than 1, of course. This is like 10 to the minus 24, okay, without units, okay? So the kinetic energy of the Earth, it gains some kinetic energy while it's falling. Well, this is falling, the Earth is gaining some kinetic energy, but it is completely negligible. Okay, thank you so much. I hope that you enjoy these things of adding the Earth that no one does, and see you in the next time. Bye. Thank you.